In this channel, we've looked at MOE models, mixture of experts, versus dense models. And the trade-off has always been that the MOE models tend to be much faster, but the dense models tend to be more intelligent and more capable. One model in particular has really impressed me, and that is Qwen 3.6 27B dense. This is a fantastic model to use as a code assistant. But because it's a dense model, all 27 billion of its parameters have to fire every time you ask it a question or ask it to do something. And that tends to make it much slower than the MOE models. Can we speed it up a little bit? Can we narrow the gap? I'm not going to pretend that we can make a dense model as fast as an MOE model, but we can narrow the gap in performance and tune it so that it's not quite as painfully slow. Let's take a look at this.
No place like localhost. No place like localhost.
All right, let's start with the baseline reading. I am going to load Qwen 3.6 27B. This is a dense model. I'm going to load it at Q4. And I'm going to load it entirely on one GPU. Let's just get a baseline reading with the model loaded on a single GPU. Start it up like this. Now, if we slide over to NV top, we see that card 1 has not done anything. Card 2 is now sitting with 17 gigs of memory usage. That is that model loaded entirely onto that card. If we go to the web UI and ask my favorite testing question, what does the transient keyword do in Java? And fire that off, it starts thinking. And if we go back and look at the terminal while it's working, we can see that we're getting about 21 tokens per second, give or take. This is a good baseline reading. I loaded it with all default settings, no surprises, nothing unusual. Okay, so let's kill the server and let's start over. I'm going to, this time, load a slightly larger version of Qwen. This is Q6. So the model file is now about 22, 23 gigabytes instead of 17 gigabytes, same context window size, and I'm still going to use default settings. But this time, I'm not saying CUDA visible devices equals 1. I'm just going to start it up. And if we slide over to NV top now, we see that card 1 is using about 8 gigs of VRAM, and card 2 is using just under 16 gigs of VRAM. That's 24 gigs combined across the two cards. Great. So we go back and ask the same question, and now we get 18 tokens per second. So we drop down by 3 or 4 tokens per second. Why? There's overhead. Well, I mean, first of all, it's a larger model. There's an extra 5 gigabytes of stuff to work with. But also, we've got overhead of splitting that model across two cards. The cards have to communicate with each other. And in the case of Saturn in the corner over there, it means they've got to communicate using a PCIe Gen 4 X4 system bus. I refer you to this episode if you want more details on the hardware setup that we're using. But basically, we're limited to that PCIe bus. I don't have NVLink set up between these two cards, so they can only talk to each other through the PCIe bus, and there's overhead involved in that. Okay, can we speed that up a little bit? I didn't give llama-server any specific instructions as to how to split that model, so by default it does a layer split. These models are divided into layers, and by default llama-server will just say, okay, fine, I'm going to take the first 20 layers and put it onto card 1, and the second 20 layers put it onto card 2, and the two cards can just deal with it. There's other ways to do this. We can do a tensor split. This gets a little bit more involved. I'm not going to pretend I understand this at a very deep level, but it's a smarter way of splitting the model. It involves a slightly different communication strategy between the two cards. Let's try this. So let's start it up again. This time I'm going to specify one extra option, and that is tensor split 1,2. 1,2 refers to the ratio of how we're going to divvy up the model between these two cards. And because one of my cards has twice as much VRAM as the other one, I feel like 1,2 is a pretty good ratio. So let's start that up. If we slide over to NV top, we see that the memory breakdown is more or less the same. Just under 8 gigs on card 1, just under 16 gigs on card 2, 24 gigs total. Great. And if we go back to the web UI, we should see the benefits of the tensor split versus the layer split, right? So if I start this process, we're going to see a huge improvement, right? Let's go and take a look at the speeds that we're getting, and we are getting exactly what we saw before, just over 18 tokens per second. But why? Why? I thought tensor split was way more efficient than layer split. Why aren't we seeing that here? Well, it is more efficient, but only in certain use cases. The value of tensor split, you see the benefit of that when you're doing what's called prompt prefill. This is ingesting data into the model, as opposed to this, where I'm sitting here asking it questions and getting it to answer me. This is generation. The benefits of the tensor split are not really evident here. So for this particular use case, a tensor split doesn't really get you anywhere. The net effect is so small that it's basically, it doesn't make any difference here. Okay, this would speed it up if we were doing something heavily involving prompt prefill. I'm not going to get into that because my typical use case for this is this. I want to get data out of the model. I don't care about putting data into the model. So what can we do to speed up generation? What can we do to make this thing output stuff more rapidly? Well, it turns out there's something called MTP, multi-token prediction. This is where there's an extra layer in the model, the head. I don't know why they call it a head, but it guesses what the next couple of tokens are going to be at a time. And the model just has to say, yeah, I think that looks right, I'm going to use it. Or, no, I think that's wrong, I'm going to compute the next token myself. And the guess is correct often enough that we see a huge speed bonus in generation speed. And if that sounds familiar to you, it's because it's a newer and better version of an older technique called speculative decoding. This is where you used to run a smaller model alongside a larger model, and the small model was just there to guess what the next token is, and the larger model would just approve or reject those guesses. And it speeds it up a little bit. MTP is a better version of this. The head layer, because it's part of the larger model itself, it shares the same KV cache, and it can do this much more efficiently. Speed increases of up to 50% or even more are possible with this. Now, just to confuse the issue a little bit, sometimes this is an extra download. If we go to Hugging Face real quick, let's look at Gemma. The Gemma models, if we zoom in here, we see that there's an extra smaller download option here labeled MTP. This is the actual head layer that you can download separately, and you can tell llama-server about it. The Qwen models are trained with the head layer already built into them. So it's one download, and you don't have to tell llama-server where the head layer is, because it's right there in the ggov file that you downloaded. There's pluses and minuses either way. With Gemma's approach, if you're not using MTP, you don't suffer the VRAM penalty of loading that extra head layer into VRAM. With Qwen, because it's part of the ggov file, you're loading it into VRAM whether you're using MTP or not. So you pay an extra VRAM penalty, but the convenience is that it's there if you decide to enable MTP. It's just an extra couple of parameters. Let's take a look at that. So it looks like this. We can ignore NP1 for now. We'll come back to that in a minute. We specify that we want to use MTP by giving it the draft MTP argument here. And then we can optionally give it a number between 1 and 6. This is, I think it's the number of tokens that it's going to guess at a time. You have to play with this number, trial and error, to figure out what works best for you. I find 2 is pretty good, but it might vary depending on your hardware. So play with that a little bit and just see what you get. Let's fire this up. If we slide over to NVTop, it looks like nothing has changed. We're still using just under 8 gigs of VRAM on card 1 and just under 16 on card 2. It looks like the same exact thing. But let's go back and ask our testing question again, and let's see what happens. 36, 33, 35, 36. We doubled it. It went from 18 to 36. It's a drastic improvement, which is great for generation speed. If this is what you're using the local LLM for, to generate stuff, holy cow, this is a major speed up, and you notice the benefits of this immediately. A task that would have taken 10 minutes before will now take 5 minutes with no other changes. All we did was add a couple of options, and bam, we doubled our speed just like that. It's amazing. So I know what you're thinking. You're sitting there thinking, what's the catch? You know, because there's always a catch. You can't just get a double speed bonus for nothing, right? I mean, there's got to be a trade-off, right? Well, yeah, there is. Let's go back to Hugging Face. And let's look at, there's a footnote here that's very easy to miss, but it's vitally important to understand this. We see right off the bat, mmproj is not supported with MTP. What's mmproj? A few episodes ago, we looked at image input. We looked at an application that can use a local LLM to understand and tag images for us. That's great. That involves mmproj. And as of the time I'm filming this, mmproj is unfortunately not supported with MTP. It's one or the other. So if you want to do image input, you have to disable MTP, which means you don't get that speed bonus. The other thing here that's easy to miss is values of NP greater than 1 are not supported with MTP. What is NP? NP is the number of things that the local LLM can do in parallel. Let's go back here. Let's actually start 2 tabs at the same time. Well, I'm going to say, what does the transient keyword do in Java? And this tab is going to start answering that question. And over here, I'm going to say, hello, how are you? And it's not answering me. Is it hung? Did it crash? What's going on? It's busy is what's going on. With NP of 1, the LLM can only do one thing at a time. This one is not crashed, it's not hung, it's just waiting. It's waiting for that other question to finish answering. The LLM can't do more than one thing at a time when you've got NP set to 1. Now, if you're sitting at a web browser typing questions, maybe that's not a big deal, right? But if you're doing things agentically or in code, where you're using multiple threads to hit the LLM at the same time, this is a problem because it means that only one of your threads can be serviced at a time and the others are just going to sit on the line waiting. It's still spinning here waiting for this first one to finish. That's a problem. So the trade-off is, I mean, yeah, great, you get a double speed bonus. That's amazing, but you lose the ability to understand images and you lose the ability for the LLM to do more than one thing at a time, which may or may not be a deal breaker depending on what you're doing with it. Now, I should point out that llama.cpp is changing rapidly, and it may be that they will eventually fix these two limitations. These are limitations right now. It doesn't mean they're always going to be limitations. So by the time you're watching this video in the future, maybe they've already fixed that. That's great. But as of the time that I'm filming this, that's the trade-off. If you want that speed boost that comes with MTP, you got to give up image understanding and parallelism. Parallelogram? You got to give up the ability to do multiple things at the same time. So there you go. It's a crash course on MTP. It's a huge speed boost for certain use cases if you're willing to live with the drawbacks of it. The most important thing is just to be aware of those drawbacks, what they are, and what the trade-off is. And there you go. I hope that information is useful. We will see you next time. I'm not going to pretend that we can make a dense model as fast as an MOE model. I don't think that's possible. But I shouldn't say that because who knows, right? If this sounds familiar to you, it's because it's a newer and better version of an older technique called... What was it called? I don't remember.